Have you ever wondered if light can be in two places at once, or if observation changes reality itself? Prepare to have your mind gently stretched as we unravel one of physics' most puzzling and fascinating phenomena. The double-slit experiment with light demonstrates that light behaves as both a wave and a particle, a concept known as wave-particle duality. When light passes through two tiny slits, it creates an interference pattern on a screen behind, just like waves in water. However, when we try to observe which slit each individual photon passes through, the light behaves like individual particles, and the interference pattern disappears. This peculiar behavior arises from the quantum nature of reality. At its most fundamental level, light is not simply a wave or a particle, but something more complex that exhibits characteristics of both depending on how we interact with it. When light is not being observed, its quantum wave function allows it to explore all possible paths simultaneously, creating the wave-like interference pattern. This is a superposition of states. The act of measurement, or observation, collapses this wave function, forcing the light to choose a definite path, thus behaving as a particle. This phenomenon showcases the probabilistic and indeterminate nature of the quantum world, where possibilities are the rule until measurement defines reality. Even a single photon, if left unobserved, will interfere with itself, hinting at an intrinsic wave nature that spans multiple locations. To understand this visually, imagine firing tiny cannonballs at two openings. They would just pass through one or the other and make two distinct piles. Now imagine water waves. They would spread out after passing through the openings and create an intricate pattern of crests and troughs where they overlap. Light, when unobserved, acts like those water waves. When observed, it acts like the cannonballs. This means that to interpret quantum phenomena, we must abandon our classical expectations of discrete, observable objects at all times and embrace a world of probabilities until a measurement is made. This experiment was originally performed by Thomas Young in 1801, long before quantum mechanics, using sunlight and observing its wave properties. It was later adapted to demonstrate quantum effects with individual particles. A particularly mind-bending aspect is that this wave-particle duality is not unique to light. Even electrons, atoms, and molecules, when fired one by one through double slits, exhibit the same interference pattern as if they too are exploring multiple paths simultaneously before measurement. This universal characteristic points to a deep, underlying principle of the universe at its smallest scales. Understanding the double-slit experiment helps us appreciate that the universe at its most fundamental level operates on principles very different from our everyday experience. It teaches us that reality is far more subtle and interconnected than it appears, where observation itself plays a pivotal role in shaping what we perceive. This experiment continues to be a cornerstone of quantum mechanics, challenging our intuitions and opening new avenues for understanding the very fabric of existence.